So what I want to do is I want to talk about how to find A inverse mod M. In other words, we're going to start by solving AX is congruent to 1 mod M. And from what we saw above, what we saw previously, we know that this has a solution. So A inverse mod M exists if and only if the greatest common divisor of A and M divides 1. And that's going to happen if and only if the greatest common divisor of A and M is 1, because the only number that divides 1 is 1, and of course, -1, but the greatest common divisor is positive. So the greatest common divisor of A and M is 1. That'll be the only time when A has a multiplicative inverse. So therefore, what we just said, I'm going to state as a proposition. By the way, this is how real math is done. You do the work, you kind of think about what did we just prove, and then you state what you proved. This is completely backwards to how most textbooks, including our lecture notes, are written. But what we just proved was the following. It turns out that A inverse mod M exists if and only if, so if and only if A and M are relatively prime. Okay, so A inverse mod M exists if and only if A and M are relatively prime. That's really what we just proved in these few lines here, plus using what we know before. What we're going to focus on in this video is how do we find, so how to find A inverse mod M. Okay, so that's going to be our focus. How do we find this multiplicative inverse? Assuming that it exists. Of course, if it doesn't exist, we're done. There is nothing to find. But assume that A and M are relatively prime. How do you find A inverse mod M? So here's going to be our process. If A and M are relatively prime, so if A and M, let me just write that a little bit better so it's a little bit more legible. If A and M are relatively prime, then we know from Bézou's little theorem that there exist Bézou coefficients, then there exists, let's just say that there exists integers x and y, where ax plus my is equal to 1. And if that's the case, actually, let me, just because we're talking about congruences, I realize that there might be a slight way to misinterpret this. So let me change our x and y to s and t, but we're still just talking about Bézou coefficients. But there exist integers s and t where as plus mt is equal to 1. This is something that we've seen before, and we've actually done some practice using the Euclidean algorithm and finding these Bézou coefficients. So if A and M are relatively prime, we can write as plus mt equals 1 for some integers s and t. And in particular, it turns out that as plus mt, if it's equal to 1, well, then it's congruent to 1 with any modulus, in particular mod m. And so that implies that as plus mt is congruent to 1 mod m, because not only are they congruent, they're actually equal. So when you subtract them, you get 0. Any value m divides 0, so this is a something that's true. Okay, so this is true for all m. And in particular, m mod m is 0. So this tells you that as is congruent to 1 mod m. So in other words, s, this number s, that Bézou coefficient that we found before, is exactly what we were looking for. That's the multiplicative inverse of A mod m. So s is congruent to A inverse. This notation, by the way, doesn't really mean anything other than inverse. And this is a notation that's borrowed from kind of elementary algebra, meaning that when you find, even when we did this above, if I just scoot back up to the notes here, when we were talking about finding the multiplicative inverse of 4, right, we write that as 1/4, as we well know from algebra. So we use that same to the -1 notation just to denote an inverse. So that's, again, just notation that's borrowed from the elementary algebra way, the usual way of doing things. Okay, so to find the inverse, the multiplicative inverse of A mod M, you first find Bezout coefficients. It turns out that the Bezout coefficient, the thing that you multiply A by, is going to be the multiplicative inverse of A mod M. Okay, so in the next video, we'll do some examples of this.